And moving on, we're going to go on to a little bit more with the product and quotient rule, but we're also going to talk about higher order derivatives today and do some other fun examples. So first, higher order derivatives. This is something I did mention earlier with some of our problems when we talked about position, velocity, and acceleration, and I mentioned that velocity is the derivative of position and acceleration is the derivative of velocity, which means that acceleration is the second derivative of position. And so that's what we're going to talk about today, a little bit with notation, as well as just figuring out how to do it. So if y equals f of x, then the first derivative is f prime of x, which we write as dy dx, or y prime. These are the common ways in which we write it. There are other ways as well, we know. The second derivative is f double prime of x, which we would write as d squared y dx squared. This isn't saying that we're squaring the function, that's why it's important to understand the notation. It's saying the second derivative. Or we can write y double prime. The third derivative would be f triple prime x equals d to the third y over dx to the third. Again, it's not saying cube. This notation means the third derivative, or we could say y triple prime. Once we go past the third derivative, then we just use numbers for the notation instead of keep writing primes. So the fourth derivative would be f4 in parentheses of x equal, or d to the 4y over dx to the 4, or y to the parentheses 4. Again, this is not saying raised to the fourth power now, it is saying the fourth derivative. So I want you to go ahead and find if f of x is x to the fourth plus 3x squared minus 8, I want you to find the first, the second, the third, and the fourth derivative. Don't overthink it if you're confused, just keep taking the derivative. So pause the video, unpause when you're ready to check your work. Okay, so f prime of x is 4x cubed plus 6x. We're just using our power rule for each term. F double prime of x, again, just use your power rule again, is 12x squared plus 6. F triple prime of x is just 24x. And the fourth derivative of x is 24. What would the fifth derivative be? Or the sixth derivative in this case? So after this, well, think about what this is saying. So the fourth derivative is just the horizontal line, y equals 24. So what is the slope of that? Well, the slope of that is 0. So the fifth derivative is going to be 0, because any tangent line to this line would have a slope of 0. Blew your mind, I know. Okay, so now taking some of the stuff that we learned yesterday, I want you to find the second derivative of f of x. Simplify it as well. Pause the video, unpause when you're ready to check your work. Alright, so you should get f double prime of x, or the second derivative of f of x, is negative 4 over the quantity x plus 1 cubed. Now, if you didn't get that, let's look at the work. So, first derivative, quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Multiply out the numerator. So I get 2x squared plus 4x plus 2 minus x squared minus 2x plus 1. Combine like terms, and then first derivative would be x squared plus 2x plus 3 over the quantity x plus 1 squared. You could also write it as x squared plus 2x plus 3 over x squared plus 2x plus 1. And this is the form that we're going to need to use to take the second derivative. If I just asked you to find the first derivative, what I have here would be perfectly acceptable and in most cases actually preferred. So now to do the second derivative, we have to do the quotient rule again with what I have over here in yellow. So bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Multiply out the numerator, and I get 2x cubed plus 2x squared plus 4x squared plus 4x plus 2x plus 2 minus 2x cubed minus 2x squared minus 4x squared minus 4x minus 6x minus 6. Most things cancel. Very nice. The bottom is x squared plus 2x plus 1, quantity squared. So the numerator becomes negative 4x minus 4 over x squared plus 2x plus 1, quantity squared. But I notice that I can factor out a negative 4 in the numerator, and that leaves me with an x plus 1. Once I recognize that, then I remember or recognize that x squared plus 2x plus 1 is actually x plus 1 squared. So the denominator is actually x plus 1 to the fourth. So the x plus 1 and the x plus 1 to the fourth reduce to just an x plus 1 to the third in the denominator, and bam, we have our answer. Did you see that coming from the beginning? You're lying if you say yes. Next one. I want you to develop a general rule for any derivative, that's what the n is representing, so n could be 1, 2, 3, 4, 5, 6, and so on, of x, given f of x equals 1 over x. So find the first few derivatives of this and try to come up with a rule that fits that pattern. If you're not sure what I'm talking about, just find the first few derivatives and then unpause the video, and then we can discuss the pattern. By discuss, I mean I'll talk about it. So pause the video now, find the first few derivatives, and see if you can come up with a pattern. And by first few, I mean find at least the fourth. Oh, one other thing before you go about doing this, do not use the quotient rule for something like this. Yes, it will work, but it is an incredible waste of time. You want to treat this as f of x equals x to the negative 1. If you use the quotient rule for a problem like this on a test or a quiz, I'm going to write a really nasty note, and it's going to take you longer than necessary to do the problem, and your simplification is going to be more difficult. Don't do it. Okay, now pause the video and find the first 4 derivatives and a pattern. Okay, so the first derivative, we should get negative 1x to the negative 2, or negative 1 over x squared. The second derivative, we should get 2x to the negative third, or 2 over x cubed. Third derivative, we should get negative 6x to the negative fourth, or negative 6 over x to the fourth. And the fourth derivative, we should get 24x to the negative fifth. Or, sorry, I didn't write that one. 24 over x to the fifth. So now we want to look for patterns. So it's important that we at least found the fourth, because then you might have seen a pattern of 1, 2, 6, and you could probably come up with a lot of different ideas for how those numbers are changing. But then once you see the 24, it really narrows down our choices. So what I noticed was, one, the sign changes. So I start off negative, then the next one's positive, then negative, then positive, and I can see without actually finding the fifth derivative that the next one would be negative, and so on. Then I also noticed the coefficients. So the coefficients were 1, 2, 6, 24, and so on. The next coefficient would have been 5 times 24. So where are those numbers coming from? Well, we'll discuss that in a second. And then the third pattern is the easiest one, is the exponents are increasing by 1. Okay, so let's go back to discussing, well, these numbers are increasing 1, 2, 4, 6, and 24. Well, where did those come from? Notice the first one, the coefficient was 1 of the function, and I multiplied that by a 1. So that stayed 1. Now I multiplied it by a 2, so it became 2. Now I multiplied the 2 by a 3, so it became 6. Now I multiplied the 6 by a 4, so it became 24. So what am I actually doing? Well, I multiplied 1 times 1 to get 1. I multiplied 1 times 2 to get 2. I multiplied 1 times 2 times 3 to get 6. And I multiplied 1 times 2 times 3 times 4 to get 24. So what is happening? Well, this is factorial. So whatever n is, the derivative, so in this case 4, or the third derivative would be 3, then this coefficient is n factorial. So let's start to write our derivative, or our pattern. F to the nth derivative, or the nth derivative of x is going to have an n factorial in the numerator. And then let's also talk about the exponent increase. Well, that's going to be x over n plus 1. Now, how do we deal with the sign change? So you may or may not remember this trick, but there's a trick on getting signs to alternate positive to negative. This had to do with when you did sequences. back in AATH. So -1 to the nth power. So if I multiply -1 to the first, it's negative, -1 squared is positive, -1 cubed is negative, and so on. So the nth derivative of the function f of x equals 1 over x is n factorial times -1 to the n over x to the n plus 1. Good times. It's not something you need to memorize, but it's something that you should be able to come up with on your own now that you've seen it. Okay, next. So we're going to use this function here, this graph that I've drawn. So you want to draw something similar, or just use this. And you want to figure out or label points A, B, C, D, E, and F on the graph. Point A is a point on the curve where the derivative is negative. B is a point on the curve where the value of the function is negative. C is a point on the curve where the derivative is largest. D is a point on the curve where the derivative is 0. And E and F are different points on the curve where the derivative is about the same. So some of these have many correct answers or ranges of answers, but I want you to look at that graph and then try to label these points. So pause the video, unpause when you're ready to check your work. Okay, so this is what I came up with. So A, remember A was a point where, A is a point on the curve where the derivative is negative. Well, what's going to make the derivative negative is if the function has a negative slope, or is decreasing. So here, the function is decreasing, and here, the function is decreasing. So anywhere along those spots, A could be labeled. B is a point on the curve where the function is negative. So where is the function negative? Well, it's negative when it's below the x-axis. C is a point on the curve where the derivative is largest. What is going to make the derivative largest? Well, the derivative is the slope of the tangent line. So where is the function the steepest and increasing? That's probably somewhere right around here. D is a point on the curve where the derivative is 0, so that's going to be at a maximum or a minimum. So we could also have D down here as well. So any of those three locations. And E and F are different points on the curve where the derivative is about the same, so that's where it looks as if the function is parallel or would have about the same slope. And so that's maybe here and here, it looks about the same. Alright, next one. A child inflates a balloon, admires it for a while, and then lets the air out at a constant rate. If V of t gives the volume of a balloon at time t, then the graph below represents V prime of t. At what time does the child begin to inflate the balloon, finish inflating the balloon, begin to let the air out, and how would the graph of V prime of t be different if the child had alternated between pinching and releasing the open end of the balloon to release the air? So again, recognize that the graph here is V prime of t. So what does that mean? The rate of change of the volume with respect to time. So I want you to find or label the points A, B, C, and then draw a picture of what D would look like. Pause the video, unpause when you're ready to check your work. Okay, so remember this function that's drawn here is the rate of change of the volume, so the volume starts to increase at this point. So that's going to be when they begin to inflate the balloon, and then it stops increasing here. The rate stops changing at this point, so that's B, where we finish inflating the balloon, nothing is happening, and then here is where we begin to let air out, and then this is going to be the point where air is done being let out. What I drew here in yellow would be something what the graph would look like had the child been pinching and releasing to release the air, because we would decrease in volume but then stop, and then decrease in volume and then stop decreasing in volume, and decrease in volume, and so on. And remember, it's rate of change. That's what this graph is that we're looking at. Alright, there are two more problems that I want to do, so we're going to stop this video here and we'll go on to part 2. Don't worry, they don't take very long, but they are important examples.